So moving on, can we take the logarithm base b of the cube root of x squared plus 2 over x squared times x plus 2 squared, write it as a sum and difference expressing all powers of factors? So it's really the same kind of thing. There's one step we have to be a little careful of. So first, we're going to break it up as the log of the numerator minus the log of the denominator. The denominator can be expressed as the log of x squared plus the log of x plus 2 squared, but that's all in the denominator. So notice that this minus sign distributes across this entire thing. So across this sum, I have a minus sign, which means I'm going to end up subtracting both of them. This is a really easy mistake to make. A lot of people get very used to saying, oh, turn a quotient into a minus, turn a product into a plus, and they just say log of this minus log of this plus log of that. And they would make that mistake of not distributing the minus sign across the entire denominator. So try not to be that person. Okay, but continuing, now I can start bringing powers out as factors. So that power of 1/3, the power of 2, the power of 2 all come out. And now we finished. There's nothing to do here. This is not an input squared, because I've got that plus 2 added on, so I can't do anything with that exponent of 2. Okay. Can we do this in the other way? Suppose I've got various logarithms. They all have the same base. That's very, very important. In A and C, they're both, every term is of base B, and in part B, every term has base E. So everything in the expression has the same base. But can I combine them back into a single logarithm? You just have to do the same steps, but backwards. So the last thing we had done was bring down powers as factors. So the first thing we're going to do is put that multiplier, or that factor of 3, back inside as a power. We may as well call 2 cubed 8. And now I have a sum of 2 logarithms, and I have log of 5 times 8, or log of 40. So as I had mentioned at the end of the previous video, you can use logarithms of prime numbers and these tricks to compute logarithms of any other number you want. So for part B, first things first, bring in that power of 2/3. Now 27 to the 2/3 is 9. And the way you see this without a calculator or anything is that 27 is 3 cubed. So therefore 27 to the 2/3 is 3 cubed to the 2/3, use the product property of exponents. This becomes 3 times 2/3. The 3's cancel, you get 3 squared, which is 9. So that's where that came from. 6 squared minus 9 is, of course, just 27 to begin with. Then we have the natural log of 9 minus the log of 27. So I can express it as a quotient, which simplifies to 1/3. You could then call this the log of 1 minus the log of 3. And remember that the log of 1 is 0. You can also get right from here to here by saying this is the log of 3 to the minus 1, and then I can bring that minus 1 out as a factor and write it like this. Which version is correct? There isn't really a correct one. The goal here was just to get a single logarithmic expression. So honestly, at this stage right here, you have a single logarithm. Everything after that is just decorative. Okay, the last one, we had these terms. So again, can we combine them all into a single logarithm? So the first sum, log of x squared plus 4 plus log of 4, we bring that in as a product. Then we bring in that next x as part of the product, and then we bring in, the 7 as a quotient. And there's not really much to do after this point. Okay, so there are various properties of logarithms. So again, the base a has to be positive and not 1. Well, it is a function, so if I plugged in the same number, if m is n, then the log of m is the log of n. Plug in the same number twice, get out the same output. It is a genuine function. But it also is a one-to-one function. Okay. If I got out the same thing, then I must have plugged in the same thing. And think back to the graph. Okay. Assuming that a is bigger than 1, the graph of the logarithmic function looks like this. Sorry, log base a of x. It's an increasing function. It's one-to-one. It has an inverse. In fact, we already know what the inverse is. It's a to the x. Okay, and similarly, if a is less than 1, it already has an inverse function. The log base a of x has an inverse function, so it had to have been one-to-one. And if the function is one-to-one, that exactly means if you got out the same thing, then you plugged in the same thing. So let's try to figure out how to work with logarithms whose base isn't 10 or e. Again, most calculators can give you common logs and natural logs, but that's it. Many newer ones do have a sort of function where it'll be like you input this log base a b button, and it prompts you for two things, and you enter in the base and the input. But maybe your calculator doesn't have that, and you don't need it. So here's how you would do this using only one reference logarithm, maybe the common log, base 10, or maybe the natural log, base e. So it really means 4 to what power equals 17. This is just converting, letting my unknown be y and converting it into an exponential. Okay. Now 4 squared is 16 and 4 cubed is 64. So 4 to the what is 17, something in between 2 and 3. It's probably a lot closer to 2 than it is to 3, but that's about as accurate as we can be with this argument. Okay. But what we can do is, since 4 to the y equals 17, we can take a logarithm of both sides, whether that's the common log or the natural log, and we're going with the natural log. So since 4 to the y is 17, the natural log of 4 to the y is the natural log of 17. Bring down that exponent and divide. And now, since your calculator can give you natural logs, you just ask what's the natural log of 17 over the natural log of 4, and you get about 2.04. So indeed, it was between 2 and 3, and it was a lot closer to 2 than it was to 3. This suggests that you never really need to use any base other than whatever you want, okay? And this is the change of base formula. If you have a logarithm in a base that you don't like, but you would like to work with a different base, whether this base b be 10 or e, and in math it's usually e, but for calculators it's usually 10. Doesn't matter, you can use anything you want. We have this formula, okay, that the log base a of m can be replaced with the log of your chosen base of m divided by the log of your chosen base of the old base a. And the reason this formula works is exactly the same as was just done. Whatever the log base a of m is, if I call it y, I convert this to an exponential, I get a to the y equals m. I can then take the logarithm base b of both sides. I can then use the exponent property, call this y times the log base b of a equals the log base b of m, and then if I divide by log base b of a, we get exactly that formula right there. Because remember, y was the term I started with, log base a of m. So if you're using base 10, you get this formula here, common log. If you're using the natural base, you get this formula right here, natural log. It works for any base you want. It's just that 10 and e are the most common to use. So using either common or natural logs, approximate both of these things that have very unusual. Log base 7 isn't that weird, but log base root 3, that's pretty strange. So get 2 decimal point approximations for each. I'll wait. So hopefully we've done these. So using the change of base formula, if we use the log base 10, we could write it like this, which works out to about 2.03. If you use natural log, you'd have natural log 52 over natural log 7, and you'd have exactly the same result. And for part B, here's the natural log version, it's the same thing. For part B, it's really the same process, it's just we have a root 7 and a root 3, and you should end up with 1.77, no matter which way you did it, with common logs or with natural logs. Okay, so that's the end of this section. Come back for the next section. We will continue discussing logarithms and exponential functions. What we're working towards are some really, really handy applications to important real-life scenarios. We just need to get through a bit more of the background first.